Let's dive right into this explainer and explore the absolute battery revolution that's about to transform our world. We hear a ton about electric vehicles and renewable energy all the time, but the real beating heart of all this tech, it's the battery. And right now, we are literally standing on the precipice of a massive shift. With traditional lithium-ion batteries basically hitting their performance limits, and with their core materials being both super expensive and supply constrained, we have to ask a pretty serious question. What actually comes next? I mean, we need technologies that use earth-abundant, dirt-cheap minerals, but that still possess the high energy density capable of delivering massive, long-distance ranges. To really grasp the urgency here, just look at the global market reality. China's massive $120 billion outbound investment surge has largely locked in the global supply of critical minerals. And honestly, this massive move is acting as a massive catalyst worldwide. It's essentially forcing the rest of the globe to accelerate alternative, resource-abundant battery innovation just to keep up.
So here is our roadmap for today to demystify all these complex technologies. We're going to start with the catalyst. Why look beyond lithium? Then we'll hit phase 1, grid and budget. After that, phase 2, the solid state. Then phase 3, long-range flight. Next up is the aluminum air wildcard. And finally, we'll wrap up with the affordable era arrives.
Okay, kicking things off with section 1, the catalyst. Why look beyond lithium? Let's map out our timeline for the next 10 years of energy storage. So it's really helpful to view this as a journey through 3 distinct phases. We're not just talking about one single battery of the future here. We are transitioning from budget-friendly grid solutions that we can actually implement today in phase 1, moving through premium scaling in phase 2, all the way to some truly sci-fi ultralight transport by 2036 in phase 3. Moving right along to phase 1, grid and budget. Let's explore the immediate, near-term technologies that are commercially ready to ease the strain on our wallets and our power grids. Now, the contrast between lithium and sodium is absolutely wild. Automakers like BYD and CAT-TL are already mass-producing sodium-ion cells for budget city cars. The secret? They're swapping out that supply-constrained lithium for simple, dirt-cheap rock salt. Now, sure, they have a lower energy density, around 175 watt-hours per kilogram, but get this. They function flawlessly at minus 40 degrees Celsius where standard EVs completely fail. They offer unparalleled safety, and they slash costs by an incredible 70%. It is hands down the ultimate winner for affordable urban mobility. And the projected growth for energy storage is just massive. We're talking about exceeding 1,643 gigawatt-hours by 2035 at a 28% compound annual growth rate. Because as we bring more solar and wind online, we desperately need to store that power. Sodium is great for that, but there's another tech that's a total game changer for heavy-duty stationary demand: iron-air batteries. To really understand the mechanics of iron-air, think of reversible rusting. I mean, iron is the cheapest, most abundant structural metal on Earth, right? The battery actually breathes in oxygen to rust the iron, which discharges energy. Then it uses electricity from the grid to unrust it, charging it back up. Now, they are physically huge and bulky, so no, you can't put them in a car, but they cost less than 1/10 the price of lithium-ion. Companies like Form Energy are already deploying these to major grids, providing incredibly cheap power to keep your whole town running on renewables for days. All right, let's transition to phase 2, the solid state. This covers that midterm scaling from 2027 to 2032. 10,000 charge cycles. That is a staggering target, but that's exactly what BYD is aiming for with their sulfide-based solid-state batteries. The core breakthrough here is basically the definitive holy grail of EV tech. They replace the flammable liquid electrolyte you find in current batteries with a solid ceramic or sulfide matrix. This lets them use pure lithium metal anodes for extreme energy density, targeting over 1,000-kilometer range with literally zero risk of thermal runaway fires. But, yeah, there's always a catch, right? When it comes to practical implementation, these batteries are incredibly expensive to manufacture right now. At 1.6 to 2.2 yuan per watt-hour, they're 3 to 5 times the price of mainstream liquid batteries. The manufacturing process requires high-purity inert gas environments and super complex high-pressure compression. Because of that sky-high cost, they won't go into regular cars first. They're going to launch in premium, cost-insensitive niches. Think electric vertical takeoff aircraft or even humanoid robots, way before they ever hit your driveway. Which brings us to phase 3, long-range flight. Let's dive into the long-term maturation for aviation, and ultralight transport post-2030. Let's talk about lithium sulfur. Sulfur is a zero-cost industrial byproduct of oil refining, which is amazing because it completely eliminates the need for expensive cobalt and nickel. Plus, these batteries offer double the energy density of high-end lithium-ion. But researchers have a major hurdle to clear first, the polysulfide shuttle effect. Basically, the sulfur kind of eats itself by dissolving into the battery's liquid components, completely destroying the unit after just a few hundred charges. The brilliant fix? Using solid-state electrolytes or specialized nanomaterial layers to trap that sulfur, which could allow for a 1,000-plus kilometer range at a fraction of today's cost. Also in this ultralight tier, we have something called carbon fiber structural cells. Instead of cramming a super heavy battery block inside a car frame, this engineering approach transforms the actual body panels, the roof, and the doors into the battery itself. Breakthroughs out of Chalmers University using partially carbonized carbon fibers allow the material to be structurally rigid while simultaneously storing electrons. It creates what they call massless energy. While the cell density itself is actually a bit lower, shedding all that massive curb weight from traditional battery casings dramatically amplifies the vehicle's efficiency and range. Next up is Section 5, the aluminum air wildcard. This is our wild, deep future tech offering extreme energy density. So the crucial takeaway here is this staggering number, 1,500. Aluminum air holds the absolute highest theoretical energy density of all the technologies we've looked at today, sitting at around 4.5 kilowatt hours per kilogram. In a standard vehicle, this translates to a massive 1,500 to 2,000 kilometer range on a single pack. That practically matches the range of traditional combustion engines. The chemistry behind it is essentially a breathing battery. Instead of a closed, sealed cell, the aluminum anode acts as the fuel. The battery breathes in oxygen from the outside atmosphere, which reacts to break water down into hydroxide, releasing a huge amount of electricity in the process. And the best part? Aluminum is incredibly cheap and already widely recycled on a global scale. But, again with the catch, the trade-off for this incredible range is how you refill it. You can't just plug this thing into your garage wall overnight to electronically recharge it. When the aluminum anode degrades, it turns into aluminum hydroxide. So to recharge your car, you actually have to physically swap out the depleted metal plates or the electrolyte every few thousand kilometers. Yet, even with that physical swapping hurdle, we are looking at explosive projected growth for the aluminum air market. It's expected to scale from $1.77 billion today to over $7.6 billion by 2035. Its main practical use in the near term is acting as a range extender for electric vehicles. Automakers can shrink the size of the main lithium-ion battery and install a secondary aluminum air system right alongside it, ready to kick in when you need that massive extra distance. Finally, Section 6, the affordable era arrives. Let's look at exactly how and when all this complex chemical engineering actually reaches our wallets. The industry expects to hit the magic 1 yuan per watt-hour threshold, which is the price point where these advanced batteries actually match today's standard costs, around the year 2030. And they'll achieve this largely by moving away from these small, slow lab processes and scaling up the continuous roll-to-roll mass production of materials like lithium sulfide. In fact, one company alone is targeting 50,000 tons of annual capacity by 2030 just to force these prices down. To tie this all directly back to your daily life, the future isn't just one single battery type to rule them all. It's a diversified ecosystem. You'll likely buy a dirt-cheap sodium-ion car for your quick city commutes. You'll rent or eventually buy a solid-state EV for those super safe 1,000-kilometer road trips. Your local utility company will rely on massive iron air setups to keep your town powered continuously by the sun. And when you fly, you'll be lifted by ultralight structural or lithium sulfur cells. So with this incredible decadal roadmap unfolding right before us, shifting us away from scarce materials and toward abundant, high-performance energy, which of these sci-fi battery breakthroughs are you most excited to see actually hit the market? Think about how you drive today. Are you waiting for the budget-friendly sodium-ion or holding out for that massive aluminum air range? Thanks so much for joining me on this explainer, and definitely keep your eyes on the horizon.